Hello everyone, here back again with another circuit that's very useful to use it in a lot of closed loop systems. This is a discrete transistor based PWM generator which will allow you to generate frequencies from about as low as 100 hertz to about 500 kilohertz based PWM control for all sorts of applications such as DC to DC converters, motor speed controllers, and anywhere where you use PWM control basically. So this circuit generates fixed frequency PWM that you can set the duty cycle from 0% all the way to 100%. And the good thing about this circuit is it's a fixed frequency. And a lot of circuits that you see online, maybe on the internet or in some electronic books using discrete transistors, as you vary the duty cycle, the frequency also changes. And in a lot of applications, that is not desirable. So basically what this circuit allows you to do is you can generate a fixed frequency PWM that you can vary from 0% to 100%. So basically in the next series of videos, maybe about 2 or 3 videos that I'll make, I'll describe how the circuit works, how it operates, and how each component value was chosen and how it was designed. And I'll show you a quick demonstration in this video how it works as it controls 12 volt brushed DC motor, and basically show you its usefulness. And in this specific case, I'm using in an open loop configuration. I'm not using in a closed loop configuration, but you can use this circuit in a, like I said, in a closed loop environment with a negative feedback to maybe measure the quantity that you want to control on the item that you're controlling. For example, for this case, if it's a DC motor, as long as you can generate a proportional voltage that is proportional to the speed of the motor, you can feed that proportional voltage back into this circuit to maintain a specific speed. Or if you want to use this in a DC to DC converter, let's say you maintaining a specific voltage at the output, so you can measure that, you can feed that back to here and control the duty cycle from, like I said, from 0 to 100% based on the load on the output of that DC to DC converter. So this circuit is very useful. So if we quickly describe the circuit, again, like I said, in a couple videos after this, I'll go into detail of how I designed each section. But this section, this circuit has 3 sections. It's got the oscillator where I'm generating a ramp signal, and that ramp signal is fed into a section that controls the duty cycle, and that duty cycle is controlled into an output buffer. That output buffer is fed into a level shifter circuit, where that level shifter, you can use any kind of voltage here to control whatever you need. In this specific case, I'm using 5 volts for my control circuit, and then for my actual DC motor controller here, the drive electronics into the motor, I'm using 12 volts. In fact, you can use this in a maybe in a system where you want galvanic isolation between the control circuit and the drive electronics. You can replace this transistor with an optocoupler, and it will give you like a galvanically isolated output that you can control the duty cycle on, right? So you can use that. Maybe in future videos I might be able to demonstrate that. So the circuit is actually shown here. It's built here. So if I remove the schematic for a second here, and it's actually built here. You can see our oscillator section is over here. We got our duty cycle control over here. We got a frequency trim here. We can trim the frequency. Of course, it's a fixed frequency, but once we trim it, it's fixed as the duty cycle changes. And we got 2 pots here in total there's 3 pots in this circuit. I'll describe it in the schematic in a second, but we got 3 pots here. This pot here controls the frequency trim. This controls the duty cycle. It's a 1-turn pot. This is a turn pot for the frequency control. And I got here a 1 meg pot that gives me a range control of this duty cycle pot. Basically, this is a 1-turn pot, so the full range of this pot, going from minimum resistance to maximum resistance, I can adjust it to map the 0% duty cycle to the minimum resistance of this pot, and then the maximum resistance will be mapped to the 100% of the duty cycles, thereby giving me a nice resolution when I vary my duty cycle. Again, this is my power supply. I'm using the 5 volts for the control section, and then the 12 volts for the drive electronics here. I'm using a 12 volt motor here mounted here. In a second, we'll demonstrate how the circuit operates, but before I do that, I'll give you a quick demonstration of how the circuit operates right now. Like I said, I've trimmed the frequency to about 10 kilohertz, and right now it's putting 7.5% duty cycle, so we can go all the way from 0 duty cycle. Again, I'm triggering on the pulses, so that's why the triggering is lost. So, and you can see the ramp that's used to generate the PWM. But anyway, if you notice at the bottom, my duty cycle changes from 0% all the way to 100%, and now the pulses are lost, so again my triggering is lost. But anyway, so now if I set my frequency, my duty cycle to as low as I can, maybe about here, about 1%. You can see here, that's where the duty cycle is, 1%. Yeah, so if I quickly bring the circuit back, and I'll show you where the frequency trimming is done. Frequency trimming is done by this pot here. It's a turn pot, and it is part of the current source here that feeds the capacitor here. And basically I can set the current that flows into it, thereby controlling the charging rate of the capacitor, allowing me to change the frequency. And this pot here controls the duty. It's a 10K pot, and I got 2 1K resistors here, kind of giving me a way to calibrate the range from the minimum resistance to maximum resistance to map to 0% PWM to 100% PWM. And then this pot also helps me to do that as well. Okay, so shall we demonstrate the circuit? I'm going to hook up my motor, the negative supply, until it is disconnected. So I'm going to connect it, and I'm going to quickly show you in an open loop configuration how the speed is varied. Now, I'm not able to load my motor here, but let's say if I was able to load my motor and I was able to measure my speed on this motor, I can feed it back into here, measure the speed here, convert it to voltage, and that voltage is proportional to the speed. That could be fed back into my PWM controller, and that would maintain a specific speed in this case. So you can use this in a closed loop environment. So let's set up our motor and I'll give you a quick demonstration.